the important QRS complex from the ECG. And I want to interact after that. Yeah. So what is the electrocardiogram? As we know, our computer works on a clock cycle. Same way, we are also conditioned on a clock cycle. The heart pumps rhythmically. As a result, all the activities takes place in the human body. There are many systems present in the human body, maybe cardiovascular system, respiratory system, neurological system, etc. So, yeah, all these activities are conditioned using the heartbeats. Heart is an organ which supplies oxygen to different parts of the human body, and it will help in circulation. Okay, every cell in the human body requires oxygen and nutrients for its survival to carry out different functions. So heart anatomy can be seen here. Aorta is the main blood vessel. Then you have right atrium, right ventricle, left ventricle. And as a result of this electrical activity, we will find P, Q, R, S, T, and U waves, as can be seen here. Okay, so I'm just going to explain. Yeah, this is a PQRST we can see in the ECG. So in the heart, there is a node called, uh, we have a node in the heart, we call it as SA node that is situated here, where I placed the mark. And this is called the AV node. We have two important nodes. One is sinoatrial node, another is atrioventricular node. Sinoatrial node is located here, and atrioventricular node is located here. So it is a simple experiment which we have gone through in basic science or somewhere in high school. That a potato, there is a potato, some space is made on one side, and it is immersed in a salty water. So what happens is the salt water enters into the potato through the cell membranes. So same way, in our heart also there is a SCN node, and there are different ions at different sides of the cell membrane. So, and there are some channels in the cell membrane through which these molecules will pass. Okay, and because of the change in action potential or change in the electrical uh, ions present on both the sides of the cell membrane, we will get a potential. You know, it is simply like a process, like a capacitor, how you model. So one kind of ions are accumulated in the one side of the cell membrane, another kind of ions on the other side of the cell membrane. This results into electric potential. So that happens at the SA node. So because of that electric impulse, we call it as action potential. It is also called as action potential. So it will propagate to various parts of the heart like this. This is your SA node, and here you have AV node, and this is called bundle of His, and these are called Purkinje fibers. And you can see here how electric rhythm generates. As the heart beats SA node, then it comes to AV node, and through there it will conduct to bundle of His, and then Purkinje fibers. And correspondingly, you can see the ECG, how it originates. Okay. One beat of ECG consists of various intervals as well as various amplitudes. So important intervals are PR interval, ST interval, then we have QT interval, then QRS interval. And in the same way, we have different amplitudes like P, Q, R, S, E, and U. There are different amplitudes, and the scales are given. This is how a typical ECG looks like. So intervals, same thing we have covered. Yeah. So in detail, it is given. J point is this. J point means once the amplitude reduces, after S, it will increase where it cuts the isoelectric line. Isoelectric line means zero potential line. Okay. The y-axis is zero throughout, and that is called isoelectric point. Okay. So in order to detect the heart disease, Hello? Hello, whether I'm audible?
Yes, sir.
Okay, hope I'm audible. Okay.
Yes,
Yeah,
sir. Now
we were
audible.
we were discussing about heart disease detection and using machine learning. Uh, yeah. So reasons for heart disease are some of the risk factors listed here. Then coming, why heart disease detection is required using machine learning. So due to abnormal heart rhythm, arrhythmia occurs. So fibrillations in flutter are very life-threatening. So there are two kinds of chambers in the heart, atria and ventricle. And atrial fibrillation uh, is dangerous when fibrillation continues. So it can lead into atrial flutter. During fibrillations, the heart will not beat rhythmically. Instead, it will simply vibrate trapezoidally. Some blood will flow in the blood vessels, and all the cells in the body will not get good amount of oxygen and nutrients. And therefore, the patient feels tired when he is having atrial fibrillation. In diagnosing arrhythmia, expert cardiologist subjectivity is required. In the sense, when a cardiologist sees electrocardiogram pattern and the clinical symptoms, based on that he will come and arrive at a diagnosis, whether it is atrial fibrillation or flutter or any coronary artery disease, etc., can be identified using ECG itself. And yeah, and atrial fibrillation and atrial flutter, they are commonly occurring atrial arrhythmias. Then other chamber, what we have is the ventricle. Ventricular fibrillations are very rare. Even ventricular flutter also very rare. In diagnosing arrhythmia, doctor subjectivity is involved, and taking the ECG and marking every point in the ECG is very tedious and will take a lot of time. It is a cumbersome procedure. So in arrhythmia, different kinds of beats are available. So 24 hours ECG, if you monitor, there are more than 1 lakh beats present in that ECG. So automation of marking every peak in the ECG becomes very difficult. So automation of the procedure using artificial intelligence and machine learning is a solution for that. So this is a simple methodology where ECG can be processed. So you can remove the noise from the ECG, then QRS complex has to be detected, then lot of data needs to be segmented, then the data size has to be reduced, we apply principal component analysis, and finally, we can classify the ECG into one of 5 beats. So they are normal, right bundle branch block, atrial premature contraction, and ventricular premature contraction. So first stage in any ECG processing system is noise removal. Maybe it is a pacemaker, maybe it is a defibrillator, maybe it is a remote monitoring. First step is unwanted components in the signal are to be removed. So they are I'll be discussing mainly on noise removal and QRS complex detection. These dimensionality reduction and classification I'm not going to discuss. And these two stages are required for any machine learning method, including your neural network, KNN, even if you want to do ensemble classifiers, or even deep learning also, you require these two steps at the beginning. So I'll be discussing them in detail. Okay. So this is the database, MITBH arrhythmia database. I won't go much into it. It is a 48 different signals are there in this database. There are 24 hour 48 signals we will have, uh, and each signal is for half an hour duration. So total we'll have more than 1 lakh beats in that ECG, and some samples are taken from this ECG and considered for the analysis. 10,000 beats are considered in the normal, then left bundle branch block another 8,000, and so on. And totally 34,989 beats are considered in this study. So the 5 beats are can be represented like this. The first signal is normal, second is left bundle branch block, third is the right bundle branch block, lateral premature contraction and ventricular premature contraction. Okay, let us go to noise removal. We'll see how to remove the noise present in the ECG. We can use a number of methods possible. We can use filtering based on Fourier transform. We can also go for wavelet transform, both continuous also we can use, or discrete also we can use. Then we can also use other time frequency representations like bispectrum, cumulant. Many representations are used to derive the or remove the noise from the ECG signal. And every method has its own advantage as well as its own demerits. So we are discussing in detail about discrete wavelet transform based noise removal in the ECG. Okay. So we have seen this MITBH database is sampled at 360 Hertz as sampling frequency. When the data is sampled with a given frequency, maximum frequency component present in it can be half of the sampling frequency. You cannot represent any higher frequency component which is more than half of the sampling frequency using your Fourier filters. So we can decompose the signal using discrete wavelet transform. This way we can decompose. We have the original ECG signal having a number of samples, which is decomposed into two subbands. Subband means frequency bands. The original signal will have all the frequencies present, and the original band of frequencies is divided into two bands. We call them as subbands. So one of them is high pass filter, another is the low pass filter. Upper one is the G is the low pass filter, and H is the high pass filter. So this process has to be continued. So original signal is decomposed into G and H. Then again, H is decomposed into another two subsets, and that process is continued. So this subband decomposition continues. You can continue it to any depth. So level 0, you have the original signal. Level 1, you have the low pass and high pass filters that is further decomposed and it continues. Okay, so simple way of denoising in Fourier when the different bands required do not have common frequencies, we can go for the Fourier transform. So what you can do is you can compute the Fourier transform of a signal, then you can find out bands which are in which you have unwanted frequency components only, and you don't have wanted frequency components in that. So in that case, all the coefficients present in the transform, you can make them 0, and then you can compute the inverse Fourier transform, and you can display that inverse Fourier transform signal. So noise will be removed, and this is valid only when you have the noise occurs in different bands and doesn't overlap signal frequencies. If signal and noise, if they occupy the same frequencies, then you cannot use the Fourier filtering. You need to go to the wavelet filtering. Okay. So we can decompose the frequency bands into number of subbands. Since our signal consists of our sampling frequency is 360 Hertz, as a result, first approximation will contain 0 to 90 Hertz, and detail will be 90 to 180 Hertz. And this again divides approximation or the low pass filter. Output is further divided into low and high frequencies. 0 to 45 Hertz is approximation band, 45 to 90 is the second detail band. And this process is continued up to 9 levels. I'm audible? Some noise I'm hearing in the background. So ECG can be decomposed with multiple subbands. Seeing these subbands, we have decomposed the ECG into 9 different subbands. Some people are discussing that. So seeing this ECG signal, various bands, we require only the marked bands only. What we are considering is 22.5 till 45 hertz is the third detail subband, and we can have on all these bands.
ये वो है ना क्या बोलता है
Yes. Okay. Okay. These many subbands we require, and other subbands we don't require. So once we decompose the ECG into discrete wavelet transform, we can consider only these subbands and all other subband, whatever coefficients we will get, so make them, force them to zero, and then compute the inverse wavelet transform, discrete wavelet transform, we'll get the denoise. So the DWT reconstruction is shown like this, dividing the
उन्होंने कहा मुझे रूम चाहिए 2-3 दिन के लिए ना तो मैंने कहा 2-3 दिन के लिए जब वो यहाँ पर आए थे ना तो कॉलेज के हॉस्टल में रहते थे
आपने मुझे क्यों नहीं बताया मेरे पीछे पीछे घूम रहा था
background noise is
पंकज सर के पास बैठे थे तो उन्होंने बोला पंकज सर ने मैम के पास भी रूम है तो मैंने कहा
we
कि
have
चलो 2-3 दिन
decomposed
के
the
लिए
ECG signal up to 9
तो उन्होंने
levels.
कहा 2-3
So
दिन हो
9th
गए फिर
level,
उन्होंने कहा कि मैं भी
we have the
5 दिन
approximation
हो
and
गए
detail.
करते करते 10 दिन हो गए 30 दिन
Approximation,
हो गए
whatever coefficients we
फिर
have, we are making
हम अपनी
all of
फैमिली
them
में ले आए
as
साथ
zero.
में ऊपर से मुझे कह रहे कभी मेरी
All
बेडशीट
of
चेंज कर दो
zero.
3 बेडशीट चाहिए होती है कभी मुझे गर्म पानी चाहिए होता है ये चाहिए होता है
People are discussing.
झूठ बोलते हैं सर झूठ बोलते बता रही हूँ क्या वो 21 दिन बाद मैंने उनसे कहा सर मुझे खाली चाहिए एक्चुअली गर्ल शिफ्ट हो रही है यहाँ पे तो कह रहे वैसे मुझे यहाँ पे इतनी प्रॉब्लम्स हो रही हैं ये वो और ना फिर उस दिन के बाद इन्होंने ढूंढना शुरू किया रूम 3 दिन में इनको
There's
रूम
some
मिला
background listening.
थैंक्स तक नहीं बोल के गए सर मेरे फादर इन लोगों को थैंक्स तो बोल देते सुबह शाम तक तुम चाय पी रहे थे वहाँ पे खाना खा रहे थे ठीक है उनको थैंक्स भी नहीं बोला सर चाबी पकड़ाई और निकल लिए और अगले दिन से ऐसा इग्नोर मारा मुझे जैसे मैं जानते नहीं है बंदा मुझे
दरवाजा बंद करके पुलिस को बुला देते
बदतमीजी है बहुत ज्यादा अच्छा तो लायक
देखो
नहीं
वो हमारे यहाँ की कहावत है अगर लाला आए और सांप आए तो पहले लाला को मारो सही है ना
हमारे यहाँ कहावत है लाला का बच्चा कभी नहीं सच्चा
Hello, am I audible?
Sir, you're audible, but lot of disturbance is there from other audience.
Yeah, that's what. Yeah, that's what. So other audience, other people can be
Participants.
muted, and when they have doubts, they can unmute. Yeah, this is the DWT reconstruction process. Ninth level approx. We have seen that the ninth level approximation we don't want. So all the coefficients you make them zero here, and you want only the ninth level detail, eighth level detail, up to third level details, and correspondingly only those coefficients you have to keep, and all other coefficients in all other subbands you have to make them as zero, and then you have to reconstruct one by one. So this is DWT reconstruction. Okay. So DWT reconstruction gives little good performance compared to the Fourier filters, because Fourier filters, in case if the noise is present in the required in the bands which are part of signal, then if you remove them, even part of signal also will be lost. Signals will be distorted. So we need to discard. Yeah, the Fourier transform is not that efficient in denoising ECG. That's the reason we have gone to DWT based denoising. Okay. Next step is QRS complex detection and segmentation of the ECG. So a simple algorithm I'm using, Pan-Tompkins algorithm, which has a number of steps listed here. So first, the signal, denoise signal is passed through a low pass filter and high pass filter. Together they constitute band pass filter. Then we have to compute the derivative of the signal, and we have to square it, moving average integration, and finally threshold operation. So these are the 5 steps in QRS complex detection, and I'm using a traditional method used by Pan-Tompkins only. Of course, there are hundreds of methods in computing QRS complex, finding the location of the QRS complex, but I'm using this basic method. This I'll be discussing. This is the transfer function of the low pass filter. 1 minus z power minus 6 whole square divided by 1 minus z inverse whole square. So this is a transfer function which we can convert it into time domain. We will get this difference equation. Okay. So yeah, it is a IIR filter where we can see X and Y both delays are present for both X and Y. So it is a infinite impulse response filter. And if you compute its frequency response and find out the cutoff frequency, it is 11 Hertz and it will have a gain of 36 and group delay of 6 samples. Okay. So gain means output will be 36 times large in magnitude compared to the input. And there is a group delay of 6 samples. In the same way, we can have a filter. The transfer function is this: minus 1 plus 32 z power minus 16 plus z power minus 32 divided by 1 plus z inverse. This is a transfer function. We can compute its inverse z transform to get this time domain representation. So cutoff frequency is 5 Hertz, gain is 32, and group delay is 16 samples here. Okay, then we are passing it through a derivative filter. The transfer function of the derivative filter is given here. So you can see that there are no denominator. So it is a FIR filter. Derivative filter is a FIR filter. It is not IIR filter. So if you can compute its inverse Z transform, you will get this difference equation. And there will be group delay of 2 samples here. Even derivative is also a filter only, like low pass and high pass. Okay. Any transfer function through which you pass a signal, that becomes a filter. Okay. Then squaring operation. Okay. It is not a filter operation. It is a non-linear operation. All the filtering operations are linear, which we have considered so far. So output is equal to square of the input, and it doesn't have any memory in the sense present output depends only on the present input. It doesn't depend on the past inputs. It's a non-linear operation. If you plot x versus y, it looks like a parabola. It is a square quadratic curve. It is not a linear curve. And no group delay is incurred here. Present in output is equal to present input square. There is no delay occurs here. It emphasizes higher amplitudes and de-emphasizes low amplitudes. Some example is given. I have a number called 0.1. If I square it, I will get 0.01. And I have a larger number 2. If I square it, it will be 4. So what it does, a large number, it will increase its magnitude, and a small number, it will reduce the magnitude of that. So when you have a signal, when you get a peak and there are lower noise in the plot, so low amplitudes it will remove and high amplitudes it will amplify. This is why squaring is used here. Yeah, and finally we are applying moving window integration. It is again a low pass filter. Most of the noise is removed in the previous stage where we have implemented squaring operation. But now we have to have a smooth curve the output. So we are doing moving window integration, and this is the input output relation of the moving window filter. So n is the number of samples in the integrator window. It varies. The window width should be 150 milliseconds, and depending on the different sampling frequency, you will get different number of samples. If the signal is sampled at 360 Hertz, you will have 150 millisecond window, which is 54 samples here. Once you compute moving window integration, you can finally apply a threshold to the data. So threshold is applied to the data, and the QRS complex corresponds to the rising edge of the integration waveform. Based on this, we are choosing a threshold value, which is we are fixing a threshold and thresholding the ECG signal. So the thresholding operation is given like this. If x of n is more than a threshold, make the output 0, sorry, output 1, otherwise make it 0. So if the value is more than threshold, you plot it as 1, and if it is less than the threshold, put it as 0. Yeah, this is how the results look. First signal which we are seeing is the original ECG signal. Then we are passing it through high pass filter, low pass filter. Then we are computing the derivative. Then we are making the square, and finally moving window integration. You can just refer this figure. The first row is the original signal. Second row will be the high pass filter output, where we can see that some low frequencies are not there. Okay. So after high pass filter, we are getting some variations. Then again, we have to perform low pass filtering. That time we'll get the signal like this. And these two operations together can be called as band pass filter. Any doubts? Yeah. Then figure D is our derivative output. Derivative filter output is this. And next is the squaring operation. So whatever negative values you have, they will be put on the positive side. And larger values are amplified. And these variations, smaller variations, which you can see, these are reduced in their amplitude. So we can see that we have a rising edge, it attains a peak, and then it will decrease. And we don't have any other values here after the squaring operation. And finally, we have to compute moving window integration, where the rising edge of the moving window integrator corresponds to this QRS complex after compensating the group delays. Just refer this. Okay. Yeah. Now this is we have to find out this particular point, the rising edge of the moving integrator output. That we are computing here. We can write in the program some heuristics that if the value is less than 0.003 or 0.005 and the present value is less, next value is higher. So that point we have to mark. We have to give a condition we have to put a for loop, and inside that for loop we should have a if condition, and we have to say if the value is lesser than a particular threshold and the next sample is also a low value, then it is not a point. So the present value should be low value and next value should be higher, and that point is the rising edge. So that has to be computed, and then you have to add all the group delay. 1 second, I'm telling you. Different filters you are using: band, low pass, high pass, derivative filtering, and moving window integrator. Each filter gives a given delay, and you have to add all the group delays, and those many samples you have to go back. After processing, after some output we are getting, that needs to be adjusted for the total group delay, and that point corresponds to the QRS complex. So this is how we can detect the QRS complex from the ECG, and it is the simplest method, Pan-Tompkins algorithm. And we can have a number of other algorithms also, like wavelet based denoising is also possible. Then various ensemble mode decomposition also people have used. A number of hundreds of methods are there for QRS complex detection. So I've demonstrated only one of them. Okay, so we can discuss any doubts are there. So anything, any queries, I'm here to address. Meanwhile, I'm thankful to the management and principal, HOD, and faculty for giving me this opportunity to present in your workshop. Any doubts are there, I can address now. Yeah, I want to interact the participants. Yeah, if you have any questions, you can just ask.
Dear participants, your interaction is highly appreciated. Here we are very great to have Dr. Roshan Joyce.
Thank you. Yeah, if participants have any doubts, they can ask. Any interaction can have. Somebody has asked where the database can be obtained. Data sets for AI, ML or deep learning. Okay. So data are available. Every application, most applications, open source data is available today. So when you do the literature survey for your paper, when you are doing literature survey for your work, you find some of the methods proposed by various authors, and in that they mention which database they had used. So that source you can refer, and day by day, new open source data is available, which you can just find out from the research papers. Recent research papers you can find out, or you can directly search in the Google for data on any particular aspect. You can search and search it. And what I had used is the MIT BIH arrhythmia database. So it is available in physionet.org, and it is a physionet.org is a large repository of data, physiological as well as image data also available there. And more than 1,000 people have completed their PhD using the physionet data itself. It's a vast data. Okay. And standard data for it depends on the application and particular modality you are using. Say I'm using, I want ECG data to be classified for arrhythmia. I took MIT BIH arrhythmia database. Okay. You can have any database for that reason. And I didn't test with the noise. Adding noise, I didn't test. Somebody has asked whether you tested for adding some given noise and its performance of. I didn't test any noise. I didn't apply any noise and remove. But some of the signals were noisy. As they acquired, there were some noise in that signal. So that has to be removed. And noise adds from many sources. When the ECG is measured, when the electrodes are placed, if a patient just nods his head or moves some part of the body, that will add some unwanted electromyogram on top of ECG. And that is unwanted, we have to remove it. Yeah, any doubts you can ask. Yeah, we can discuss anything. Yes, I can share the slides. I will give it to the organizer, then collect later. Yeah, any doubts are there, we can discuss.
Dr. Roshan sir,
Yeah.
we are very great to have you, your expertise.